Finish up some notes for chapter 5 here. We've been talking about gases. Now we're going to flip the switch and start talking about liquids and solids. Unlike gases, these particles are going to be close together and therefore will be attracted to each other. And so I have these close particles. There should be some kind of attraction between those particles, and that's where these intermolecular forces come into play. Right, so liquids and solids are a little bit different than gases. They are attracted to each other, so that affects their properties. And those forces involve interactions between these partial charges we're going to talk about. And so there's 3 different kinds of intermolecular forces. We just need to go through those. So first you have this dipole-dipole interaction. So we've talked about this already in the standpoint that a molecule that has a hydrogen and a chlorine is not necessarily nonpolar, right? A dipole-dipole interaction is between polar molecules, and we talked about how chlorine pulls electrons better than hydrogen does. So we had that separation of charges. That chlorine was negative, partially negative, whereas the hydrogen was positive. So if you had 2 of those molecules, right, and you might flip those, right, both of which have those partial charges, you have forces of attraction between the hydrogen and the chlorine on both sides. And those are dipole-dipole interactions. So since I have a separation of charge, since I have a dipole, I have this attraction between these molecules. Now that attraction is said to be intermediate in strength, right? So these different attractions we'll talk about, some of them are stronger than others, right? The hydrogen bond, my next example, is stronger than that dipole-dipole interaction. It is actually technically a dipole-dipole interaction. But when we're talking about a water molecule, when you're talking about oxygen, nitrogen, or fluorine, they are so good at pulling electrons from those hydrogens that there's an even bigger apparent charge on these atoms. So the attraction between these 2 water molecules, which would be considered a hydrogen bond. We gotta finish drawing the second one. This attraction from hydrogen to oxygen here is bigger than the attraction above between the chlorine and hydrogen. And that's just because oxygen is so much more electronegative than chlorine is. So these ones are strong relative to those dipole-dipole interactions. But technically, a hydrogen bond is a dipole-dipole interaction. They're very similar things. You have 2 polar molecules that are attracted to each other because of those partial charges. And finally, we have these London dispersion forces. Right? This one's different than the other 2. In this case, I'm going to have nonpolar molecules that are attracting other nonpolar molecules. So that one's a little bit harder to explain. Right? What essentially has to happen is, say I have these 2 hydrogen molecules, right? One hydrogen bonded to another. There could be a weak attraction between those 2 molecules, but it's dependent on some random movement of electrons. Remember, anytime I have a bond, it's a shared pair of electrons that goes around both atoms. But at any given time, it's actually possible for both electrons to be on the same side. So at that moment, this side has a partial negative charge. The other side would have a partial positive charge. It doesn't last for very long. In fact, it'll flip the next second. But at any given brief period of time, you can have a separation of charge. The difference with those polar molecules was that when I had that shared pair of electrons around these 2 atoms here, the 2 electrons are almost always around that chlorine, which is why it carries that negative charge, that partial negative charge. And it's more likely to be negative than the hydrogen is. But for these nonpolar molecules, neither side is more likely to be negative than the other, so it just flip-flops back and forth, essentially. It is possible for both electrons to split and for this thing to be neutral, but right at any given moment, one side could be positive, the other side could be negative. And what that does is it'll influence another molecule. I also have a pair of electrons, excuse me, let me black there. I also have another pair of electrons around this other molecule, this shared pair that are going back and forth, right? But as long as the molecule above is partially negative on this side, that's going to influence my other molecule because negative repels negative. So I have two electrons again that are being shared in this other molecule, but as long as my hydrogen on the right in the top molecule is negative, the hydrogen on the right in my bottom molecule will actually tend to be positive because negatives repel other negatives. So these electrons go from one side to the other. They're pushed to the other side. So these interactions are different than the interactions before, right? I have a temporary dipole. This is the temporary dipole that induces a dipole in a second molecule. Because the hydrogen on the right was negative, that caused the electrons in this molecule to shift to the left, and it just keeps flip-flopping back and forth. But as long as one molecule is next to the other, it's going to influence the other, right? So there's always opposite charges. So I do have attractions between these molecules. They're just really tiny. I have an attraction between this hydrogen and this hydrogen. Same thing on the other side, because as long as one is positive, the other one has to be negative, because they just keep flipping back and forth, and they keep influencing one another. So I have this temporary dipole, I have an induced dipole. These are generally very weak attractions, but they can actually be strong because they're additive. So we're going to talk about molecules next semester that are organic, right? These long hydrocarbon chains. So all I have here are a bunch of carbons linked together, but the same idea pops up here. If I have two of these molecules, right, and every pair of electrons, I can have a dipole, right? So if this side's negative, this side has to be positive with this pair of electrons that's shared between those two carbon atoms. But since this is positive, this has to be negative, and it just keeps alternating all the way up and down. Oops, I'll make that one positive. Negative, positive, negative, positive, negative. And because it's close to the other molecule, it's going to influence the other molecule. As long as this carbon on the end is negative, this one's probably going to end up being positive. This one will end up being negative, positive, all the way up and down. And once you put all that together, this one was supposed to be positive, right? You can have a collection of attractions between carbons, right, all the way up and down this molecule. So we're assuming those are right next to each other, positives attracted to negative, and vice versa, all the way up and down. I have 1, 2, 3, 4, 5, 6, 7, 8, 9 attractions there. I only had 2 attractions between the hydrogens. So the attraction between the hydrogens was weak because there's only 2 of them. But once you get 9 of those attractions, it can end up being pretty strong. Right? That's the idea. So they're additive. The more you have, the stronger that attraction can be. So this hydrogen sample on the left would actually likely be a gas at room temperature because that attraction is very small. But this hydrocarbon on the right, with 1, 2, 3, 4, 5, 6, 7, 8, 9 carbons for those 9 attractions, is actually more likely to be a liquid and or a solid because of all that extra attraction. So we're going to talk a lot about attractive forces next semester. We need to understand how that works.